Now today's plan is to finish the discussion on buckling of columns, and we're going to move on to buckling of beam columns. And before we talk about buckling of beam columns, let's clarify a few important concepts. The first concept is about determination of change of curvature point. And we use the same concept in finding this equivalent length on example 8. So what do I mean by the change of curvature point? Let me use the more detail or much larger schematic to explain that. When we consider
Professor, there's more students trying to get in. Sorry.
All right. When we consider this fixed problem or fixed-ended, both fixed-ended column buckling problem, and after buckling, we know that the geometry is going to change. To be something like this. We say that it's going to be 90 degree here, 90 degree here, or somewhere in between, and mid-span, it should also be something like that. And this is going to change of the curvature starting from this, and change to that, comes back to here, and goes back to this. Now you have to recognize that there's a change of curvature twice in the deformation profile of this both fixed-ended column. One curvature change is from this end. Suppose we call one of them A, and the other is called B, like this. And starting from A to B, the first curvature, which is, we haven't defined whether it's X or Y, but that doesn't matter because you can notice there's a change of curvature very obviously. And here, the first curvature is going to look like this. Right? That's the first curvature. And please take notes, all right? If you don't take notes, you're not going to remember. And structural stability is not a subject that you can just learn by observing it. You have to keep your hands busy, all right? Now, another curvature change is when you look at this. All right. This is not working. There's some technical issues with my Apple Pen. Try to connect it. All right. That's another curvature, right? Which is second curvature. And the third curvature is when we move approaching to the support B. There's another curvature, which is like this. We have not defined which one is positive and which one is negative, but that doesn't matter. The point is you cannot notice that there's a change of curvature. So the points we talked about it before, about how do we use the change of curvature points to define equivalent lengths. And this is the way we do it. The intersection points between these two curvature change points is how we find out the equivalent length. And this equivalent length compared to the case of a simply supported column. And this is important. Compared to what? Compared to a simply supported column, which would like this. Suppose that the length of a simply supported column is, we call it capital L. Equivalent length means that the buckling behavior of this column is equivalent to some fraction, some portion of the length of a simply supported column. So when you define this to be the length, the equivalent length of a non-simply supported column in its buckling behavior can be defined by a ratio which is K, capital K times capital L. In other words, this ratio is just to see that if you don't have a simply supported column at hand to study its buckling, but you want to find out how can we use the buckling node from the analysis of a simply supported column buckling to the columns that you are studying, and that result can be used. So how do we make this connection? You already know that the buckling node for a simply supported column is what we call a PCR. This equals to pi squared times EI over L squared. Now this particular load is also what we call Euler's load, and has a special name called P sub E, in honor of the great mathematician Leonhard Euler. So this is just definition. Whenever we use this value or expression P sub E, that just means this. In other words, P sub E is a constant. Now, if we can find a way to convert this, then we can actually use this concept to calculate equivalent buckling node by writing this. We can say that flow is going to be something related to this one. You will keep the expressions upstairs the same, but downstairs you will replace the original length with KL. Becomes squared. So the approach that we are still using this today is to use this concept to adjust the length of the column to the level that you can reconsider boundary condition. Because the reason why these two are not the same is because boundary conditions. So that's the first clarification on how do we use this change of curvature points and to determine the equivalent length. In this case, we know that this capital K, the value of capital K in this problem, it is 1/2 or 0.5. This is what we know. Now, if we define this, we can also derive the expression of the K. Because so far it looks like this capital K is perhaps just some experimentally determined values. No, a capital K can actually be calculated. So the name of this capital K is what we call effective length factor. This capital K can be determined by what? By this calculation. If you take the square root of P sub E over the critical load of your column, you know that this PCR carries different values depending on the problems that we study. So PE, on the other hand, is a constant. Keep in mind that PE is pi squared EI over L squared. And we're going to use this definition in some examples that we will solve them today. So this is the way you can calculate effective length. That means even you don't know the effective K, but once you have found the critical load, you can use the critical load that you found and to calculate what is the equivalent effective length factor of this problem. So this is the from this definition. Another way we can also use this effective K is what? Is suppose in the problem you are provided with the effective length factor. Like what? Like if the value of K is provided. The critical load, PCR, can be found from this definition. PCR equals just simply as PE over K squared, right? That means if I give you the theoretical value of K, then you can just use the theoretical value of K to determine the PCR, which is a shortcut, right? So please pay attention to this information because on the PE exam, sometimes the problem gives you this information. It tells you that the value of K is this much and what is the critical load. Once you have the information, you should know that you don't have to go through all these force equilibrium because you can use the concept of effective length to determine critical load. And that is as simple as just this expression here.